The Pythagorean identities are probably the most useful identities of all of the ones that you're going to learn. I think that's fair to say. And they are really just you putting together a bunch of pieces that I think you already know, although two of you might have forgotten. So take a minute and review for yourself. What's the definition of tangent? How do you rewrite tangent in terms of sine and cosine? How do you write cotangent in terms of sine and cosine? Same thing for secant and cosecant. And then remember what sine and cosine mean. If this is the unit circle, so it's the radius 1 circle centered at the origin, what do sine theta and cosine theta describe about this circle? So take a minute and try and fill those out. Pause the video. You can do it. So starting in sort of reverse order here, the Sohcahtoa definition of sine and cosine. For sine, it's describing if you have a triangle like this, it's describing the opposite side over the hypotenuse. But here, the hypotenuse is length 1. So really, sine theta is describing this height, which you'll notice is the same thing as the y-coordinate of this point. So if this is xy, here sine theta is the y-coordinate. Cosine theta, if you're using Sohcahtoa, it's the adjacent side length divided by the hypotenuse. Again, the hypotenuse is 1, so if you divide by 1, that's just the adjacent length. So this is cosine theta, which you'll also notice is just the same thing as the x-coordinate of that point. So we've got cosine theta is telling us the x-coordinate, sine theta is telling us the y-coordinate. Hopefully this is review. You remember this already. Okay, what's tangent theta? This is one of those ones that you just should know. If this doesn't pop immediately into your head, and you're also planning on taking calculus, like you should really drill this until it's immediate for yourself. Cotangent, same thing. Cotangent is just the reciprocal of tangent. That's sometimes useful. Again, you should have this in your head immediately. Cotangent is just cosine over sine. So if that's not in your head immediately, that should be a goal for yourself for this unit, is to make sure that you know those cold. Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. Those are two more that we haven't used a lot, especially recently, but again, you'll need to know those dead cold for calculus. Okay, so review of the basics done. So what is this Pythagorean identity, you ask? It's really just the Pythagorean theorem rewritten using trig functions. So what's the Pythagorean theorem say? It says this side length squared plus this side length squared is the hypotenuse squared. But if we're talking about the unit circle here, this side length is cosine. Well, here let's write it in terms of x and y first. So we've got x squared plus y squared equals the hypotenuse squared, but the hypotenuse here is just 1. And now for the reasons that we just said here on the unit circle, the x-coordinate is the same thing as cosine theta. So x squared turns into cosine squared theta. Y squared turns into sine squared theta. And then 1 is still 1. Just a quick note here. If you don't remember, this squared right here is another way of saying quantity cosine theta squared. So this is just a notational thing. This is just a different way of notating cosine theta squared. Okay, so this is the first and most useful of the Pythagorean identities. Why is it useful, you ask? If you have an equation like this, you've seen these before. May look intimidating, but actually you'll notice it's got something squared plus 2 times the same thing minus 3. So you can use the blob technique to do something like this. You just define p as your blob, and then you've got p squared plus 2p minus 3, and so that's a lot more familiar now. So you can factor it and solve for p, and you get p is 1 or negative 3, but since p is the same thing as cosine, it's not possible for cosine to output negative 3, so that's not a solution. So all the solutions for theta would come from this branch, and you've done all that before. Oh dear. There we go. And you've done all that before. So obviously we have not used any identities here. So what if the problem had been a little bit different? What if we had something like this? Think for a minute, could you apply the same technique? And you really can't because we've got two different things here. We've got a sine and a cosine. So this is no longer quadratic because we can't, well, it's not quadratic within a single variable because we can't substitute the same variable in for both terms here to solve. So this is the kind of situation where it would be helpful if we could rewrite cosine as sine or rewrite sine as cosine. And that is what the Pythagorean identity lets you do. It lets you rewrite sines as cosines or vice versa. So this is only one form of the identity. You might imagine it this way. Let's try and isolate cosine squared. So we've got cosine squared. If we subtract sine squared from both sides, we've got cosine squared is 1 minus sine squared. Or we could do it the other way. We could subtract cosine squared from both sides, subtract that from both sides, and get sine squared is 1 minus cosine squared. So here you can take a cosine squared and rewrite it in terms of a sine squared, or vice versa. So if you were going to apply that technique here, let's take the cosine squared and turn it into a sine squared. Now we've got cosine squared is 1 minus sine squared, and then we've got minus sine. And so now you can distribute. Let's distribute and subtract. So now we've got 2 minus 2 sine squared theta minus sine theta equals 2. I can subtract the 2's from both sides. I can multiply by -1. So now I've got 2 sine squared theta minus sine theta equals 0. And now you can really apply the same kind of technique that you did before by substituting in blob for sine. What if we wanted to solve something like sine theta plus cosine theta equals 1? Could you apply that same identity to rewrite sine as cosine or to rewrite cosine as sine? Well, we don't have a sine squared in order to substitute, and we don't have a cosine squared. But don't let that stop you. You drive the algebra. Don't let the algebra drive you. So if you don't have the thing you want, make the thing you want. So let's pretend I want to rewrite sine as cosine. Let's make it into sine squared. And, you know, you can't just, it changes the problem if we just turn it into sine squared like that. This is no longer the same problem. So let's compensate. So sine theta is the same as root sine squared theta. Well, almost the same. We'll see in just a second. It's not quite the same. It would be the same if the output of sine were positive. If the output of sine were negative, you can think about that in just a second. So now we've rewritten sine as the square root of sine squared. So now we can apply this identity because we can rewrite sine squared as 1 minus cosine squared. So now we've got 1 minus cosine squared plus cosine theta equals 1. This is great because now we have only the same type of trig function. And so now you can start to substitute using blob. So let's call p cosine theta. Now you've got 1 minus p squared plus p equals 1. And you can start solving. Here, let's pop this over here like this. So let's see, if I wanted to solve, I need to get rid of the root, so I'll move the p over to the other side. So I've got this, and then I can square both sides. So that's 1 minus p squared, and then I could expand this, so 1 minus 2p plus p squared. Cool, and now, you know, and like now you could do it, right? You're solving a quadratic, and you know how to do that. So that's the kind of way that you will end up applying the Pythagorean identity. And there's going to be a problem in the problem set where you're going to do this the rest of the way, and also think about why this is not quite an equality, because we're possibly missing some solutions here.